Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
Thank you all for being here, despite the weather, and thank you to Myron for that introduction. And as Myron said, today I'm going to talk about optical lattices, which are a tool of atomic physics and also an interesting physical phenomenon in their own right. And as I've titled my talk, Crystals Made of Light, that's kind of how you can think of optical lattices. So, to start out with, crystals made of light. So to understand what the title means, the first thing you have to understand is what's a crystal. Now throughout this talk, I'm going to be using the word crystal and lattice pretty much interchangeably. They're almost the same thing, not quite. There are some subtle differences, but I'm not really going to get into those differences in this talk. So whenever I say crystal, I mean lattice. Whenever I say lattice, I mean crystal. And what I mean by both of those words is any repeating pattern that each repetition of the pattern is exactly the same as the previous iteration. So you can have a lattice or a crystal in various dimensions. In 1D, for example, it's just a straight line, as I've drawn here. So you have a particle, and then the same distance after that, you have another particle, and the same distance after that, another particle. And the distance between the particles is the period. Now the period is actually the distance between the beginning of the pattern and the beginning of the pattern starting over, but in the 1D case, that's the same as the distance between two particles. In the 2D case, it's a little more complicated. I drew two different versions here for you. There's a square lattice, where the particles repeat much in the same way as the 1D case, but in 2 dimensions instead of 1. And then there's a triangle, usually called a hexagonal lattice, below that, where they repeat, but this time in a triangular pattern. And then you can further expand to the 3D case. So I drew a cubic one over there. The particles are arranged in cubes, and each cube is one period of the lattice, but you can, in the 3D case, you can get a lot more complicated than that. You can have particles in the middle of your cube, you can have a tetrahedron, you can have all sorts of shapes. And in the 3D case in particular, it's important to note that a period is the size of the pattern, not the particle spacing, because you might have a few particles within your pattern. So that's a crystal. What does that have to do with light? Well, so how do you make a crystal out of light? So far I've been saying particles, 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 and that's not really much to do with light. Well, let's start with what is light? Light is a wave. What does that mean? Well, so I'm from California. When I think of waves, I think of water. So this is actually, I got this off of Wikipedia. This is a really nice illustration of waves. These waves are coming from the wake of a boat, and there are waves moving out to either side of the boat. And then in the middle, where the two different wave patterns overlap, you get a completely different pattern due to that overlap, which I'll get into in a moment, because that's really important to the whole concept of an optical lattice. But to define a wave is a periodic moving disturbance. It has a direction of propagation, and it has a direction of oscillation or vibration. So in this case, we have a wave propagating to the side, but the vibration is only up and down. So let's say this is a water wave again. If you look at a buoy in the water, or if you look at a particular water molecule, as the wave moves through, the molecule's only going to move up and down. It's not going to move side to side at all. But the disturbance itself, the disturbance itself is going to move side to side. So if one water molecule is moving up, then a little bit later, the next one next to it is going to be moving up, and then the next one next to it is going to be moving up. So that's what I mean by the disturbance moving side to side. But any given particle only moves up and down. Now, crystals made of light, let's go back to light. A light wave, very similar to a water wave. There's a direction of propagation, and there's a disturbance. And it's an electromagnetic disturbance. There's an electrical disturbance, in this case I drew it up and down, and a magnetic disturbance, in this case I drew it in and out of the screen, and they're always perpendicular to each other. And then from this we can also define a polarization, and the polarization is the same direction as the electrical vibration of your light wave. So we could just as easily have, instead of the polarization being up and down here, which we'll call vertical, it could instead be horizontal if the electric wave was pointing in and out of the screen and the magnetic wave was pointing up and down. So the last thing you need to know about waves themselves, very generally, is what happens when two waves interact with each other. So think back to that picture of the wake of the boat. Where the waves overlapped, it looked entirely different from where the waves themselves were just purely coming off the boat. So what happens when two peaks kind of collide with each other? Well, they add. And when two peaks add, you end up with a peak that's as tall as the two peaks combined. We call this constructive interference. And if you have a peak and a trough that overlap, then they combine and it flattens out. And so that's what was happening in the middle of that wake, was waves were destructively, that's what we call it, destructively interfering. So let's move on to the concept of a standing wave. A standing wave is two waves going in opposite directions. The easiest way to do this is to reflect a wave back on itself. And the standing wave, the two waves have the same wavelength, the same period to them. And so what this looks like is two waves moving in opposite directions, and they add. And you can look at the drawing of the two waves up there, and I can say they add, but you can't really visualize that. So what does a standing wave really look like? Well, I have a nice demo here where I have a string attached to a motor. The motor vibrates it, so that's how we get our wave. And then at the end, the string is fixed, so the wave reflects back. And let's see if we can get, there we go. And we get a standing wave. So this is what it looks like when you have a standing wave. So you have a part over here where the string isn't moving at all, and I can stick my fingers in and not get hit. And we call that a node. And I have a part out here where the string is vibrating a whole lot, and if I stick my finger anywhere near it, I get hit, and that's an antinode. Node and antinode. And although the wave itself is propagating this way and propagating back, the nodes and the antinodes don't move. So as far as anyone looking at this, anything caught in the middle of this is concerned, everything's standing still, and it's just a matter of this area is vibrating, this area is standing still, that area is vibrating. So what if something is stuck in the standing wave? If you have an object in a standing wave, it's going to be kind of loud. So in this case, we have, it's kind of traveling. All right, the wave isn't standing perfectly. That's a little better. Okay, so what this is there's a sound wave coming from the speaker, propagating through the tube, reflecting off the far side, and coming back, and that's our standing wave. And the tube is filled with polystyrene beads that interact with the standing wave. So the beads don't like to be around the vibrations. So they get kind of knocked away from the vibrations into the still air, and so they form a pattern, a periodic pattern, where the period is the period between the nodes of the standing wave. So effectively, the standing wave can be used to trap particles in a periodic pattern. Now, what I showed you just here, it's a periodic pattern of trapped particles, but it isn't quite a crystal. Each of those nodes had a whole plane of particles all stacked up in it. It wasn't like that single particle diagram that I drew at the beginning. But we're getting close now. We can kind of see how a standing wave would get you something that would look kind of like a crystal. Now, once again, let's go back to light. What happens to an object in a laser beam? And now here I'm not talking about standing waves at all anymore. I'm talking about just shine a laser beam on a particle. It turns out they discovered back in the 80s that if you focus a laser beam down, a small particle will tend to get trapped at the focus of the laser beam. This is called an optical tweezers. So now you can imagine with light, we can make a very similar situation to what we did with those sound waves. We can have a particle trapped, but instead of in the nodes of the standing wave, it would be in the antinodes because it likes it where there's a lot of light, as opposed to those particles that didn't like it where there was any sound vibrations. So, how do we make a standing wave of light? There are two main ways. The first we call counterpropagating, and it's basically exactly the same as the two standing waves I've just showed you. You have a wave propagating in one direction, and since this is light, it's a mirror. The laser beam reflects back on itself, and you get your standing wave. There's a second way, and it's called the crossed beam method. And so the way it works is you have two beams going in the same direction, angled a little bit with respect to each other, and it turns out where the beams overlap, you get an interference pattern, which isn't completely obvious. So I'm actually going to show you that it works. So what I have projected on the screen up here is what's called a double slit. So there's a laser beam shining through a pair of small slits that are right next to each other. And usually this experiment is used to prove the wave nature of light, because only waves interfere, which is also an important concept to keep note of. But I've already said light is a wave, and hopefully you've accepted that. So here's the proof, but more importantly, the laser beam is being split effectively into two laser beams at an angle with respect to each other by the double slit, and the two beams interfere. And that interference pattern up there, you'll notice it has stripes of light and stripes of dark, and those stripes are not moving at all. So although the beam itself is propagating forward, it's propagating from the far end of the room up to our screen here, the pattern is a standing wave that's side to side that's not moving. So that's how the crossed beam configuration works. This can be expanded to multiple dimensions. You can just as easily get, for example, here I've drawn the counterpropagating beams again. You can get counterpropagating beams side to side, and then another pair up and down, and then you have a two-dimensional grid of light spots to trap particles in. And then you can also imagine we could get a third pair of beams in, going in and out of the screen, and then we'd have a three-dimensional array, a full three-dimensional array. And then particles would hopefully be trapped in all the light spots in that array. Of course, oh wait, okay. So what's this going to look like to particles? It looks like something like this to the particles. We call this an egg crate potential. The particles like to be at the brightest spot, and so they're attracted to the brightest spot. So we call those spots wells. They look like valleys in this picture. And so then, since they're attracted to the brightest spots, they're repelled from the spots where there's no light at all, from the nodes of our standing wave. So those are like hills, and it's very much like as if the particle were on an egg crate like this, and it tended to roll away from the hills, which are the nodes of the standing wave, into the wells, which are the antinodes of the standing wave. So all the particles would fall into wells. So real life's a little messier. How do we actually get this to work? So the first thing we use to make a crossed beam lattice is a microscope objective. That's our main optical tool here. And mostly what it consists of is a lens that focuses some beams down really tight. So if we have a pair of beams spaced apart, they go through the lens, they get focused down to the same spot, and where they cross at that spot, you get your sideways standing wave, like I demonstrated a moment ago. And so if you just stick a sample in there, a sample of whatever it is you want to trap, then that sample will be subjected to the standing wave, and hopefully you will see an optical lattice. And then real life is messier still. This is what our actual setup looks like, more or less. There's a pair of downgoing beams, and that pair creates a standing wave going, in this case, in and out of the screen. There's a pair of upgoing beams, and that one creates a standing wave going side to side. And then, as it turns out, and the math on this is a little more complicated, the total interference pattern of all four beams combined also gets you a standing wave up and down. So in this way, with only four beams, we can actually get a 3D standing wave. And that's the advantage of the crossed beam pattern. And then we stick a sample, in this case, a pair of slides with some water between them and some polystyrene balls, just like those ones, floating in the water, and we can get an optical lattice. So what does it look like? It looks like this. Those are actual polystyrene beads in water, floating around, being trapped by a 3D optical lattice. And it traps them in a grid pattern, and so we have formed a crystal with our polystyrene balls. It's not quite the same as what I showed you here with the sound waves before. These polystyrene balls, they're big enough to see, they're big enough to touch and hold, they're maybe a millimeter across. The polystyrene balls in the picture here, those are 250 nanometers across. For comparison, a human hair is about 50 microns, so these are a factor of 200 smaller than a human hair. And in this case, we're using lasers. We use an infrared laser, 1 micron wavelength. And so it's the near infrared. You can't see it with your eyes, but only barely. But that does make it a little dangerous. You don't want to accidentally stick your hand in it without noticing. And we turn it up to a couple watts of power. For comparison, a laser pointer is typically between 1 and 5 milliwatts. So the lattice we use here, the laser light we use for the lattice here is about 1,000 times brighter than a laser pointer. So you really can burn something if you stick something in the beam accidentally. But the main thing is it works. We can get our crystal of trapped polystyrene beads. How else can we look at it? Well, in that picture I showed you before, it was backlit with a blue LED shining through the microscope objective into a black and white camera. But there's another way, kind of a more standard way to look at a crystal, and it's called Bragg scattering, or it's occasionally called crystallography. And Bragg scattering is meant to look at the periodic structure of a crystal. And the way it works is, let's say you have a photon of light shining down onto your crystal. It hits a particle, it scatters off, it can scatter in any direction. So I drew concentric circles to indicate scattering in any direction, and you can think of the white part of the circle as being the peak of the wave that scatters off. Okay, say you have more light coming in, several photons at once. They all hit a bunch of different particles, they all scatter off in random directions. So far, so good. But you have some peaks lining up with peaks, some troughs lining up with peaks, some troughs lining up with troughs. And so you have interference. And it turns out there are only certain angles at which you get constructive interference so that you actually get light coming out. And those angles, and people have put a lot of time into studying this, those angles can be calculated back to tell you what the exact shape was of your crystal to start with. Because those angles, the shape of the resulting Bragg scattering pattern depends entirely on the periodic nature of your lattice. So in our own experiment, the way we do it is we have a green laser, helpfully colored green on the slide, and it shines up through the microscope objective and comes in kind of at an angle with respect to our lattice, hits the lattice, and then scatters off and comes out of the objective, and then we project it onto actually a piece of lined notebook paper. So we can talk about different modes of scattering. So up there, there's one not dotted line that's labeled the 0,0 mode, and that's the unscattered light. That's the green light that just goes through the lattice, doesn't hit anything, and comes out. And then there's the 0,1 mode, which is the light that hits the lattice and gets scattered that way. And there's the 1,0 mode that hits the lattice and gets scattered perpendicular to that. And the 1,1 mode hits the lattice and gets scattered both forward and sideways. And in real life, it all works. So it's actually green light. And so this is what you see if you try to do Bragg scattering off that particular lattice up there. So there's a 0,0 mode. It's much brighter than the other modes. Most of the light doesn't scatter at all. There's a shadow in the middle, though, because some of the light does scatter and it gets blocked out from the original beam. And then there's a 1,0 mode. And so what the 1,0 mode indicates is that we have a lattice side to side. There's some sort of periodicity side to side. And the 0,1 mode indicates that we have a lattice up and down. There's some sort of periodicity up and down. With this particular setup, we can't see in and out of the screen, but there are other setups where we would be able to do that in theory. And then there's a small 1,1 mode, which is light that's scattered both sideways and upwards, which mostly just indicates that we have very strong lattice trapping, very strong periodicity on both axes. And then the last thing we can see from this fairly easily is the 1,0 mode and the 0,1 mode are each about the same distance from the 0,0 mode. And so what that means is the period of the lattice is the same in both of those directions. Now we can change the polarization of the original lattice beams, and in doing so we can change the nature of our standing wave, and so we can change the lattice potential that the particles see. And so on the picture on the left, we have changed the polarization such that we hardly get any trapping up and down, but we still get quite strong trapping side to side. And you can't really see it that well from the blue backlit picture, but the green picture, the Bragg scattered picture, you can really see that the up-down scattering peak is very small, but the side-to-side scattering peak is very bright. And then the picture on the right, you can see a lot more clearly that most of the trapping is in the up-down direction. There's very little in the left-right direction. And sure enough, the Bragg scattering peak, the up-down Bragg scattering peak is very bright, and you can barely see the left-right Bragg scattering peak at all. And so what this indicates is that, for that one, in the up-down direction, it's very strongly patterned. And in the left-right direction, there isn't really a pattern to it. It isn't as well trapped in our standing wave, so there isn't really a pattern to it. Why are we doing this? Well, these polystyrene beads, they're about 250 nanometers. We've actually done experiments ranging from about 190 nanometers to about 500 nanometers. And it's about the same size as particularly large proteins. It's about the same size as viruses. So you could imagine we could trap proteins or viruses or other biological materials in this lattice. And then, having done that, we could examine their structure. So using a green Bragg scattering beam, we only have resolution down to half the wavelength of our green light. So we only have resolution of about 250 nanometers. But if instead of green Bragg scattering light, we used X-rays, for example, which is what's commonly used when you're doing crystallography with Bragg scattering, we would have much, much, much higher resolution. So let's say we trap proteins in our optical lattice. So we have an array of proteins. And let's say we applied an electric field or something so that all the proteins are pointing in the same direction. So now we wouldn't just have a pattern that consists of a protein here, then a protein over, and a protein over, and a protein over. We would have, let's say each protein had an arm sticking out to the left. So the pattern would now also consist of an arm sticking out to the left, an arm sticking out to the left, an arm sticking out to the left. And the Bragg scattering, if it had good enough resolution, would pick that up, and it would see that pattern. So by reading back the Bragg scattering, we would be able to see what the original shape of the protein molecules were. So this would be a good technique for that. And currently, it's the way people do it is they make a kind of a bulk crystal, a rock crystal type crystal of proteins, and they do X-ray Bragg scattering on it, and that is how people look at this. But this particular setup gives more versatility with a better chance of not ruining the protein in the process. So we hope to eventually build up on this experiment and apply it toward that end. So there is a limitation to all of this, Brownian motion. So right now, these are really small particles. They're trapped in the lattice. They're kind of wobbling around a little, but they're basically trapped in the lattice. But soon, you'll see in the video, the lattice is there. The lattice is turned off, and now the particles just move around in all directions. And then the lattice gets turned back on, and they start to hop back into place, and the lattice slowly fills up. And all of that motion is what's called Brownian motion. And it's due to collisions between the water molecules and the polystyrene beads. So the water molecules are all moving around at a set velocity due to their temperature. And it's the same for us standing in air. Here we are standing in air. Air molecules are whizzing around at about 600 miles per hour, a little bit faster than a jet plane. And here we are standing here, and they hit us all the time, and they don't move us at all. We don't even notice them. And for these polystyrene beads, the water molecules are whizzing around, and they're hitting the beads. But they're not hitting them that hard. The beads are pretty big, so the beads don't move all that much. But if you have a smaller bead, the water molecule looks a bit bigger next to the bead, hits it a bit harder as far as the bead's concerned, and the bead starts to move around more. So you saw in this lattice, the beads actually jitter a little bit in the lattice. If you move to a smaller particle, the Brownian motion of the water is going to start to have a much bigger effect, and the particles are going to start jittering a lot more. So that brings us to limitations of this technique. So if you have particles that are too small, first of all, you can't see them with your camera, and that makes it really hard to align the lattice. But that's not a fundamental limitation. That's just a technical limitation. But the real fundamental limitation is Brownian motion. The particles are moving around due to the water temperature. And so let's say we have a particle that is moving really slowly, and we have our egg crate potential here. And the particle is moving really slowly toward the egg crate potential, and it just drops into the well, and it stays there. Great. That's what I've been describing so far. That's what happens to all these polystyrene beads in the size scale we're looking at. But what if the particle were coming in moving faster? What if it were coming in with some velocity and it tried to make it into the egg crate? It just bounces right out. It doesn't stay in at all. And in real life, with a real optical lattice, it might just go through the lattice instead, the same way your hand goes through a laser pointer and just ignore it altogether. So you can't have particles that are moving too fast, or they won't stay in the lattice. So that's a limitation on how small the particles can be, because as they get smaller, they move faster and faster due to the Brownian motion. Now, one solution to this is that egg carton I have over there. What if the wells were deeper? What if the sides were taller? Then the particles would stay a little better. So you can make your optical lattice wells deeper by turning up your laser power. And that works to a degree. But we found that once we turned up our lasers to about 4 watts, the polystyrene beads started to melt. So there are limitations to that as well. There's only so deep we can make our lattice. So that's it for the polystyrene beads. Now there's another regime entirely where this works. Let's say we can get very cold. Well, if we try to cool down our polystyrene beads floating in water, we can cool them down about 20 degrees Celsius till we hit the freezing point of water. And then they're going to freeze, and the lattice isn't going to do anything to them at all. But there are other things we can get much, much colder than that. There are a couple decades worth of technology on getting atoms, individual atoms, cooled down really cold. So in our case, we have an experiment where we can get our atoms to a few tens of billionths of a degree above absolute zero, a few tens of nanokelvin. That's about 100 billion times colder than room temperature. And if you look at my chart here, this is a log chart, so each big tick mark represents a factor of 10. So our experiment is down here way at the bottom. Way up in the middle of the chart is deep space, which is a couple of Kelvin. That's the coldest place in nature. And it's as much a factor of difference between deep space and our experiment as it is between deep space and the core of the sun. That's how cold we can get our experiment. So at a few tens of nanokelvin, the atoms are basically not moving at all. So we're not going to run into this Brownian motion problem anymore. As for how we get our atoms this cold, well, that would be a whole talk on its own. You can ask me that later on if you want, but that's pretty complicated. So, atoms, they're cold, but they're also small. And the smallness doesn't matter for the Brownian motion because they're so cold. But to give a sense of how small the atoms are, now we're talking a few angstroms. So we're talking another 1,000 times smaller than those polystyrene beads were in that previous experiment. And those themselves were 200 times smaller than a human hair. So that's the size scale we're now looking at. And at these sizes and at these temperatures, atoms behave quantum mechanically. So they have all sorts of weird new properties that we never see in our big macroscopic life. One of these properties, one of the coolest of these properties, is tunneling. Tunneling is where you have a particle, and with some probability, it vanishes from where it is and reappears somewhere else. And it'll even do this if there's a barrier in the way. How high the barrier is determines how likely this is to happen, but in this case, I drew a brick wall, and it would be the equivalent of a blue bouncy ball just suddenly going through a brick wall without having occupied any of the space in between. So that's one thing that atoms at this temperature can do. An optical lattice actually provides a really good way to look at tunneling because it gives you a whole bunch of little barriers, those being the nodes of your optical lattice. And so you can look at the rate at which a particle might tunnel from one lattice well to another. And there have been a lot of experiments along these lines over the years. And so this provides a really nice way to just look at quantum mechanics. So this is actually one of the original things that optical lattices were invented for, was as a tool to look at quantum physics like this. there's another neat quantum trick we can do. We can make a perfect crystal. So in that slide I showed you just before this, there was one well with 2 atoms, there was one well with no atoms, and it was all just a random distribution, because probably when it started out, you started out with a cloud of atoms, and they were randomly moving around just a little bit, and it happened that 2 were closer together, some were farther apart, and some lattice wells got filled with more, and some lattice wells didn't get filled at all. But what if you want exactly 1 per well? So in the case of the polystyrene beads earlier on, there was exactly 1 bead per well, but that's because the beads were about the same size as the well. 2 wouldn't have fit. They would have collided with each other. They just physically could not fit. In this case, the atoms are much smaller than the wells. The wells are actually about the same size. They're still about 500 nanometers between wells, just like with the polystyrene beads before. So there's plenty of room for multiple atoms. So how do you get a perfect crystal? Well, instead of just turning on your lattice all at once, you start out with your cloud and no lattice, and you turn on the lattice just a little bit. And now the atoms in the cloud like to be closer to where there are wells, and they like to be further from where there are hills. And you just slowly, slowly, slowly turn your lattice on more and more, and let the atoms fall as they will into the wells, and fall as they will away from the hills, slowly at their leisure. And if you do it that way, you end up with exactly 1 lattice per well. So in this way, you can get an absolutely perfect crystal. What's this good for? Always what you have to ask yourself. Well, for one thing, it's a novel state of matter. If you think of a real natural crystal is never going to be perfect. A crystal growing in nature, it's going to have cracks in it. It's going to have this part of the lattice is a little bit displaced compared to that part of the lattice. It's going to have impurities. It's going to have what are known as vacancies, where a certain lattice site doesn't have an atom at all. So here we have something that's very much like a natural crystal. It's made of atoms, just like a natural crystal, but it's perfect. There's exactly 1 atom per lattice site. So you can use this to test condensed matter theories, which is useful because if you know that your theories work for the perfect case, then that makes you a lot more confident to try to expand them to the flawed case of a real-life natural crystal. So it gives us a good test case here. Also, it turns out that if you make your perfect crystal the way I just described, the atoms really hate to tunnel. They really hate to travel from well to well. So you end up with what's effectively no communication between wells. So this is called a perfect insulator. There's no travel, electricity can't travel, no signal whatsoever can travel between lattice wells. So that's its own condensed matter theory to be tested out there, an actual type of object that can be predicted with condensed matter theories, but that you're never going to see in real life at all, other than in these sorts of optical lattice experiments. Now there's also a technological application, what's known as a quantum register. So you have your perfect lattice, you have 1 atom per well, and let's say you can focus a laser down and hit just 1 atom and do something to it. Let's say change its spin from spinning toward the right to spinning toward the left, or give it a little bit of momentum or some sort of energy. Do something to it. Give it a little bit of information, we'll call it. And now you can move over to a specific other atom, and you can do something to that, imprint a little bit of information on that one. And you can do this in a very controlled way. You can get to each atom separately. So then you can store information on each atom. And what you effectively have is a hard drive. So that would be a hard drive for a quantum computer. It would be basically the smallest hard drive you can get. Each bit or each qubit is an individual atom. And these atoms, as I say, they can't tunnel. There's no information traveling. It's a perfect insulator. So there's nothing to cause you to lose this information. Nothing's ever going to happen to these atoms that are sitting here. unless you do something, unless you read out the information or you imprint information on them. So this is some technology that we're not actually working on this here at University of Michigan, but various people around the world are working on using optical lattices to create a quantum register like this. So let's get to the last part of my talk. This is actually the part I like the best. The role reversal, light as crystal, matter as wave. So the title of my talk was Crystals Made of Light. And so far I've been talking to you about crystals made with light, using light to force particles to form crystals. But what about literally considering our lattice, our optical lattice, to be a crystal itself? Well, with the atoms this cold, we are in the quantum regime where matter behaves as a wave. So we can start to think of things that way and start to form analogs between the case of a crystal made of matter with light interacting with it and a crystal made of light with matter interacting with it. So let's go back to Bragg scattering. Here's basically our Bragg scattering diagram from before. We have a matter crystal, a periodic spacing of particles, and light shines onto it, scatters off of it, and the lattice periodicity, the shape of the lattice, determines the angle at which the light comes out. Well, similarly, we can have a periodic structure that's our optical lattice, and we can scatter matter waves off of it. And the matter waves scatter off, and the velocity at which they come out tells us what the periodicity of the lattice is. So when we're really doing this experiment, what we do is we accelerate a cloud of atoms through the lattice. In this case, it's a 1D counterpropagating lattice. And when the accelerating atoms reach a certain resonant velocity, they Bragg scatter off the lattice and come back out with their new Bragg scattered velocity. And it looks something like this. So this is actual matter that's been Bragg scattered off a 1D optical lattice. So you can see it looks pretty much just like our green Bragg scattered pictures from earlier in the talk. Now it's a 1D optical lattice, so you only have a 0th order, that's what I've labeled unscattered, and a 1st order, which is what I've labeled scattered. But it's really the same. And the velocity, and when we wrote a paper on this, we actually did this and made sure it all worked. The velocity of the scattered atoms comes directly from the lattice period spacing. So this is real Bragg scattering that really does measure our optical lattice. Then there's diffraction. So diffraction is where you have, let's say you have a diffraction grating is an object that consists of a whole bunch of slits evenly spaced. And when you shine a laser through it, it's fairly similar to Bragg scattering. The laser light comes through in a variety of modes, much like Bragg scattering modes. But you can see there are a lot more modes here. So this is just a green laser going through a diffraction grating, going through probably a few thousand slits, and it scatters off in this pattern. Well, diffraction grating, periodic pattern, optical lattice, periodic pattern, very similar. So we can have matter waves scattering off an optical lattice, diffraction grating. So what this picture here is, it takes a little bit of looking at to figure out what it is. Each row is a different optical lattice that was turned on for a different amount of time. So it's effectively a different diffraction grating. And so on each row you see what happens when the matter waves, the atoms, scatter off of that diffraction grating. So at the top, the lattice is barely turned on, and there's no scattering at all. But as you move down, the lattice is on for longer and longer amounts of time. And you can see the atoms really diffract off your light diffraction grating. And it starts to look a lot like what we saw a moment ago with the green light going through the physical diffraction grating. So here we once again have an exact analog between, over there, matter-based diffraction grating and light as the wave, and here, a light-based diffraction grating and matter as the waves. And finally, I'm going to show you using light as a beam splitter. So with both the Bragg scattering and the diffraction grating, we could split our matter waves into different components. So we can use that by carefully tuning it. In this case, we're using the diffraction grating because we actually found that a lot easier to tune. So we turn our lattice on briefly. Our matter wave diffracts into a few different orders. We turn it off. The matter has some momentum to it to start with, so it moves a little bit. And then we turn the lattice on again. And then now each of those components is going to diffract separately. So the middle one is going to end up with a middle one and one out to each side, and the side one's going to end up with one where it is, one going toward the middle and one to the far side, and the far side one is going to have one going to the middle, one staying where it is, and one going to its side, like that. And so now we have a bunch of different components of matter waves all overlapping with each other. And what happens when waves overlap? They interfere. So let me just point out what this really is here. This is each of those bigger circles is a component. It's a diffracted component. And within it, there are stripes, and the stripes are the interference pattern. So what we've done here is we've taken atoms. In this case, we're using rubidium, which is a shiny metal. Okay, so we've taken this shiny metal, and we've taken components of it. First of all, we've diffracted it like a wave. But we've taken components of it, and we've taken these 2 bits of metal, say, or 3 bits of metal, and we've overlapped them, which isn't normally something you can do with metal. But it worked. They overlapped. Okay, but let's say you do overlap 2 pieces of metal, you expect to end up with twice as much metal. But no, in this case, it's a wave. So we end up with, instead of just twice as much metal everywhere, we end up with stripes where there's a whole lot and stripes where there's nothing at all. And if we use a lot more atoms to start with, we can get some really spectacular interference patterns. So here we have matter overlapping with itself and interfering so that we get places where there's no matter at all. Well, what can we do with this? Well, first of all, from a fundamental physics perspective, I think this is pretty interesting. So you can probe the wave nature of matter, which isn't something you can normally access at all. And you can also learn about lattice structures in general, because you have a very perfect lattice in the form of your optical lattice. So there's a lot of fundamental physics you can do with this. But technologically speaking, you can also make what's called an atom interferometer. So what I showed you just now was an atom interferometer. It's basically you take your atoms, you split them into 2 components, you let them be apart for a little bit, then you recombine them and you look at the interference pattern. And the interference pattern, if anything happens to the atoms when the 2 components are separate, that's going to shift the interference pattern. And atoms are sensitive to just about everything. They're sensitive to magnetic fields, they're sensitive to gravitational fields, they're sensitive to motion. So if anything like that happens, so you could imagine, you could take your atom interferometer and you could put it right next to a magnet, and then the magnetic field from that magnet would shift your interference pattern. So now you have a way of measuring how strong your magnetic field is. Or you could do a flyby in an airplane, and as you fly over, say, a cave or a particularly dense set of minerals, like some ore that you might want to mine or something like that, that's going to affect your interference pattern. Or let's say you put this in a submarine or a spaceship. When your submarine or spaceship makes a turn, that's going to affect your interference pattern. So you can use this for sensors. You can use it for navigational devices. And this is still obviously several years away, but this is a technology that really is possible with these interferometers. And these interferometers are more sensitive, in particular to gravity, but also to certain sorts of motion than any sort of technology that currently exists. So, in summary, this is what I really want you to have gotten out of this talk. First, what an optical lattice is. It's quite simply a standing wave of light. Second, what it can do. It can force matter into perfect crystals. It works with large particles like polystyrene beads. It works with small particles all the way down to individual atoms as long as you get them cold enough. With it, we can demonstrate a role reversal between light and matter. And we can use this as a tool for a variety of emerging technologies. So, thank you. So let me just get my thank yous out. I'd like to thank my advisor, Georg Reidel, who's sitting in the front row here. And I'd like to thank all the people in the lab who helped out over the years. Everyone contributed something, whether it was just talking about the experiments or lending equipment. But the people in bold with stars next to their names actually contributed to the optical lattice projects. And in particular, Betty Slama did a lot of the setup for the polystyrene beads in water optical lattice experiment. And Rui Zhang did all of the role reversal of light and matter experiments with me. So in addition, I would like to thank the department, the physics department here at U of M, for inviting me to give this talk. And I'd like to thank the demo lab for setting up all these cool demos, which I hope made the talk a lot more interesting. And I'd like to thank all of you for coming and listening to my talk. So thank you very much.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.